Okay, so next we're going to talk about the sorting algorithms that we already know and how these are applied to linked lists. So we talked about linked lists and how they work, and we've talked about sorting and how that works, but we haven't put the two together. So we're going to do that by going through a couple examples. So we've talked about sorting on arrays, but you can implement sorting on linked lists in the same exact way. So we're going to start by going through insertion sort. So here's an example of an unsorted linked list. Here the nodes contain only a single integer, right? And we want to create a new list with all of those same integers, but in sorted order. So the first thing we do, we know with insertion sort, is we start with an initial list. So we have one part of, normally it's one part of our array that's unsorted and one part of our array that's sorted. But because we're working with linked lists here, we can actually have one list that's sorted and one list that's our unsorted parts. Right? So the thing we do is we take the thing off the front and we figure out where it goes in our sorted list. So here it's 4 and we know it's going into an empty list, so it just goes at the beginning. And in that case, our front pointer moves to 8, right? And 4 now points to nothing, right? So we want to make sure that points to null. And then we have to figure out where 8 goes in our sorted list. Well, it either goes before 4 or after 4. And because 8 is larger than 4, it goes after 4. So we're going to, 4 is now going to point to 8. The front is going to point to 1. And 8 is now going to point to null, right? And that's what our list looks like after that. The next thing we need to do is figure out where 1 goes, right? 1 either goes before 4, between 4 and 8, or after 8. Well, it's going to have to go here. So again, now the front of our sorted list points to 1. The front of our unsorted list points to 3. And 1 points to 4. Right? So it kind of looks like that. And if we make everything a little bit prettier, we got that. Right? We do the same thing with 3. Again, it gets pointed to there, that goes there, and now that goes there. So the thing to remember is that the order in which those pointers are updated, the order in which the next values are updated, is very important. Because once you lose pointing to something, you can't ever get it back. So if, for instance, the first thing we did was change sorted to point to 3, well, now we've lost the connection to our 1 node. Right? We no longer have a way to reference this guy. Similarly, if the first thing we did was update this pointer, right? Well, now we no longer have a reference to 7. If the first thing we did was update this pointer, we would no longer have a reference to that guy. So just like we do when we swap variable values, normally we need to sort of set this as a temp variable. Then we can, update this guy, update that guy, right? And then update that to there, right? Because we still have that pointer somewhere. If we hadn't saved the pointer, if we hadn't saved 3 somewhere, we would have lost connection to it. 7, then we know 7 needs to go here between 4 and 8. So we update the pointer there, add it back. And finally 9 goes at the very beginning. And what we're left with is now our front pointer, right? Our unsorted array, or our unsorted list, is empty. So now we have nothing left to sort. And you can see our sorted array now contains all of the elements that we started with in sorted order. right? So that was insertion sort, where we're taking the front thing from the unsorted list and figuring out where it goes in the sorted list. So what if we did the same sorting, but using selection sort, right? So remember, selection sort goes through the unsorted part of the array, or here, the unsorted list, and finds the minimum or maximum and puts it in the correct position. So it's equivalent to either find the minimum and put it at the front or find the maximum and put it at the back, right? So since we're dealing with linked lists, which you can only traverse forward, right, it's going to be easier to find the minimum and put it in the right place. So what's our algorithm going to do? So again, we have our unsorted list here, our sorted list here. Initially, the sorted list is empty. So the first thing we're going to do is we're going to run through this list and find the minimum, right? So we're going to start here and say this is temp. And we say temp dot next or temp equals temp dot next until temp equals null, and if temp dot value greater than max dot value, then max equals temp, right? So basically we're saving the node that has the maximum value, and we're going to keep traversing all the way through. Eventually we're going to end up with 9 being, well, here we need the minimum. We actually need minimum. Right? So we're going to end up with -9 being our minimum, and we're going to put that over here. Right? Whoop. There we go. So now 9 is in the correct place, and 9 is never going to move. Right? It's the very minimum of all of the things we've seen, and it's always going to stay in the same place. So then we're going to do the same thing. We're going to find the minimum up here and insert it here. But what's going to help us is if we keep a pointer, right? We keep track of the end of the sorted list, because we know we have to do a linear search to find the minimum in that guy, right? But we know we're always going to put it at the end of this list. So if we keep track of it, then we don't have to do a traversal to get there. So we know the minimum is 3. We're going to move that there. There we go. Move that there. Move 7 in, right? Update this pointer here. And shift the end, right? Now the end of this list is -3, and we know whatever the next minimum is going to be the next from there. So we do that, we find it's 1, and then 4, then 7, and 8, right? And now, once again, our unsorted list is empty. Our sorted list contains all of the elements that we saw before in sorted order. And then in that case, we could just get rid of that guy, right? We don't need the sorted end anymore. We don't need to know where the end is, because we've already sorted everything, right? Good. So the next algorithm I'm going to run through is merge sort. So I talked when we were talking about merge sort originally, how merge sort is sort of ideally used on linked lists. And that's because when we do merge sort on arrays, it's a little wonky, right? We have to figure out what range we're supposed to be sorting and where we're putting everything. Here we now have a bunch of objects, right, that are just pointing to each other. So we have our initial unsorted array here, right? Or our unsorted list. And we know that our merge sort algorithm says, well, you need to break this in half, sort this half on its own, and then sort this half on its own, and then merge them back together. Well, breaking the list in half when you're talking about a linked list is really easy. Because how do you do it? Well, we make some new pointer here, right? Second half, right? We set this next pointer to null. And then we can run merge sort on front, and we can run merge sort on second half. So that's exactly what we do. Again, it's recursive. Merge sort is recursive. So now we're making two recursive calls. One is over here on the first half. One is over here on the second half. And again, within these, we're going to split these in half. So it's going to split them right here and right here. And the same way, you break this and you set it to null, and you have some new pointer there. So now we end up with these calls. And notice that these are the same node instances that we had all the way across. We're actually, we're not moving them, we're just changing the pointers around a little bit. Right? We're changing what the next values are. And those make recursive calls in themselves until you get down to single lists, right? Lists with one value. And if the list only has one value, then it's already sorted. So then we need to start working our way back up the tree, right? So we're going to look at this pink box here, and it has two child lists that it's going to try and merge. So it needs to decide which goes first in my return structure. Is it 4 or 8? Well, 4 is smaller, so 4 goes in the list first, and then 8. Same thing over here, right? -9 goes before 7. Now we're going to remake this guy, and we're going to do it in order. Well, so we have to look at 4 and 1. Which one comes first? If we're in increasing order, it's going to be 1. And now you can see this list is empty. So once this list is empty, we can just move this whole list to the end, right? Everything that's left has to go after what's left, right? And we know it's already in sorted order. When we look at recreating this list over here, well, we need to decide, does -9 or -3 go first? Well, it's going to be -9. Now this front pointer, in this child comes over here and it points to 7. This front pointer points to -3. So which comes next? Is it 7 or -3? Well, it's going to be -3. And now again, this list is empty, so we just move 7 over. And then we can start merging this list here and this list here. So we're looking at -9 and 1. Well, -9 comes first. So we add it, move the front pointer. -3 comes next. Then 1 and 4, 7. And then now this guy is empty, so we can just take the rest of that list, which just happens to be 8. Okay? So that's how merge sort works on linked lists, right? You're taking the list, you're actually splitting it in half, and you're not having to, right, when we did it with arrays, if you actually split it in half and made 2 full calls without using ranges and things, you had to copy all the stuff out of one. But with linked lists, you don't have to copy anything. You can just split it in half and send it on its way. And then merge the lists as we bring it back. Okay, so that's sorting with linked lists. The one we didn't go over was bubble sort with linked lists. So that's something you might want to do on your own, just to see if you can try and simulate sorting using bubble sort on one of these examples.